In this problem, we have a system that is 1 meter 6 kilogram uniform rod AB pinned to 2 uniform discs, each with 0.1 meter radius and 2 kilogram mass. And it is initially at this location when theta, this angle right here, is 60 degree, and then it is released from rest. The discs roll without slipping, and we need to determine the angular velocity of the rod AB when it becomes horizontal. So this is the initial state, so state 1. And then we need to sketch out the final state. For the final state, we will have, this is actually the wall right here. We will have this disc B right here, and then we will have the rod right here, and then this is disc A. So this will be state 2. So we're going to use the principle of work energy applied to a system. So we have the total final kinetic energy of the system equals to the total initial kinetic energy plus the total work done to this system. And in this case, initially the system is at rest, so total initial kinetic energy is 0. And if we think about what forces are doing work during this process, it's actually only the weight force of the disc B and the weight force of the rod AB are doing work. So for disc A, there's no displacement of its gravitational center. Therefore, its own weight does not do any work. So this equals to the weight force of the disc, which equals to 2 kilogram times 9.81 times the displacement. So for disc B, the displacement is from here to here. So this distance right here is 1 meter times sine 60 degree. Plus the weight force of the rod AB, which is 6 times 9.81. And its displacement is from here to here. And this distance is 0.5 times 9.81, sine 60 degree. So this equals to 42.48 joule. And by the way, at this point, you probably realize that this system, during this motion, there's no non-conservative force doing work. Friction does not do work. Normal forces don't do work. There's no any other kind of external forces. So only weight force is doing work, and weight is conservative force. Therefore, if you choose not to use the principle of work and energy, but use the conservation of energy, that you will get the same results as well. So in that case, that will be the total initial potential energy plus the total initial kinetic energy equals to total final potential energy plus the total final kinetic energy. And then you will be able to get to the same conclusion that the total final kinetic energy still equals to 42.48 joule. So now, remember what we need to solve for is the angular velocity of rod AB. And then we only have one equation, that total final kinetic energy equals to 42.48, which means that we need to represent the total kinetic energy as expression of omega AB, which is our unknown. And we can only have one unknown here. Otherwise, we won't be able to solve this problem. So let's look at the final kinetic energy of state 2. Because the gravitational center of point A, of disk A, will always have, during this motion, it will always have the direction in this direction. So that's VAG, which is the linear velocity of point A. And during this motion, the linear velocity of point B is always vertical down. So for the final state, And by the way, VBG is also the linear velocity of point B on the rod AB, and VAG is also the linear velocity of point A on the rod AB. Therefore, if we try to determine the instantaneous center of zero velocity for rod AB, we will draw a line that is perpendicular to VBG, and draw another line that is perpendicular to VAG, where the intercept, which is this point right here, which is point A, and that is actually the IC for rod AB. So this point right here, point A, is also IC for rod AB. So what does that mean? It means that VA simply equals to 0. And VA also equals to omega A, which is the angular velocity of the disk A, times RA relative to ICA. So ICA is the instantaneous center of zero velocity of disk A, which is this point right here. And we know that RA-ICA is not 0. RA-ICA is actually this little distance right here, which is 0.1 meter. So if VA is 0, which is determined from rod AB, analyzing rod AB, but when we analyze disk A, VA also equals to omega A times RA-ICA, and this is not 0, so the conclusion is omega A is also 0. So omega A is also 0, which means that T2A, which is the kinetic energy of disk A at state 2, is also 0. In other words, now our summation, the total kinetic energy T2, only has two components, which is T2B, the kinetic energy of disk B, plus T2AB, the final kinetic energy of rod AB. So let's analyze T2B. T2B equals to 1/2 MB VBG squared plus 1/2 IBG omega B squared. Omega B is the angular velocity of disk B, and also we have omega AB, which is this one right here. I should have probably drawn this earlier. That is the angular velocity of the rod AB, which is our unknown. Okay, so T2B equals to 1/2 MBVBG squared. That counts for the translational part of the kinetic energy, plus 1/2 IBG. IBG is the mass moment of inertia about point B, which is the gravitational center of disk B. Omega B squared, omega B is the angular velocity. Now, how do we represent this in omega AB? Well, because point B also belongs to rod AB, therefore VBG simply equals to omega AB times RB relative to ICAB, which is 1 meter. So this simply equals to omega AB times 1 meter, still in magnitude the same as omega AB. But VBG also belongs to disk B, therefore it equals to omega B times RB ICB, and ICB is this point right here, because again the disk B is rolling without slipping. So this point right here is the ICB, and RB ICB also equals to 0.1 meter. So omega B times 0.1 meter equals to omega AB. Therefore, the conclusion can be drawn from here that omega B equals to 10 times omega AB. Lastly, T2AB equals to, because we have already found the instantaneous center of zero velocity, so we can write this directly as 1/2 I AB ICAB, too many subscripts. Either way, this one right here is the mass moment of inertia of rod AB with respect to its own instantaneous center of zero velocity, which is this point right here, point A right here, omega AB squared. So now everything is ready. We can start writing our total equation. So our total kinetic energy equals to this part right here, 1/2 times MB. MB is 2 kilogram. VBG, we just determined that VBG equals to omega AB. So omega AB squared plus 1/2 IBG, mass moment of inertia of the thin disk about its gravitational center, equals to 1/2 mr squared. So 1/2, another 1/2, m is 2 kilogram, r 0.1 squared, that is IBG part, and then omega B equals to 10 times omega AB squared. That's right here. So far, this much is the total final kinetic energy of disk B plus the total final kinetic energy of rod AB, which equals to 1/2 times this much, because it is moment of inertia about an axis passing through this point, the edge of the rod, which equals to 1/3 ml squared. 1/3 times m, 6 kilogram, L is 1 meter squared times omega AB squared. So this part right here is the total kinetic energy of the rod AB at the final state. So as you can see, in this equation, there's only one unknown, which is omega AB. So this overall equals to 2.5 omega AB squared. But don't forget, the total final kinetic energy equals to 42.48 joule. So 2.5 omega AB squared equals to 42.48 joule. So at this point, we can evaluate omega AB, and omega AB equals to 4.12 radian per second.